Oh, hi. Welcome everybody to our lab number 2 on influence of intermolecular forces on physical properties of few substances. In particular, the substances you will be working with in experiment number 2 is water, preferably distilled water, acetone, or just nail polish, or isopropyl alcohol, which is at least 91%. Those are the three substances we will be working with in experiment number 2. That is influence on intermolecular forces on the three substances I just mentioned to you. Well, let me just walk you through on what we will be working with. That is the intermolecular forces. What I want to do is look at the three types of intermolecular forces, and then from there, walk you through the experimental procedure. I just want to kind of like real quick go through the intermolecular forces. Intermolecular forces, I know it has been a while. You know, some of you may have taken the course way back, okay? And you may have forgotten about the intermolecular forces, or maybe you just got started with the chapter on solution where you covered intermolecular forces. What are intermolecular forces? What are intermolecular forces? Intermolecular forces are forces of attraction between two substances. Forces of attraction between two substances could be molecule of the same compound, such as H2O. We could say that the type of interaction between those two are intermolecular force of attraction. I'm trying to see where iPad, make sure that it's hooked up. Sorry about that. I'm just gonna go through trying to get my code here. See if it's gonna work. Hold on, see. Okay, let's see this. Right, intermolecular forces. I'm trying to load up my whiteboard so that I can write and show you the 4 types of intermolecular forces. So what I want to do is share my iPad, and you should be able to see now my whiteboard. This is what I was trying to load. The whiteboard you see on my right hand side. We should be able to look at what is going on here. All right, let's see the 4 types of intermolecular forces. 4 types of intermolecular forces. 4 types of intermolecular forces are London dispersion forces, hydrogen bonding, dipole, all right, dipole, and ion dipole. These are the 4 types of intermolecular molecular forces. We have what we call intra, all right? There is what we call intra like that. Intermolecular forces, it means the molecules between two substances in the molecular forces of attraction. Yes, so this is what I'm trying to say. The intermolecular forces, intermolecular forces. These are forces between two separate molecules. For example, H2O. This is the molecular structure of H2O. And if we have another molecule right here, all right, with hydrogens, assuming this shape, positive, negative, positive, negative for oxygen. We're going to talk about that momentarily. The type of force you see here is called intermolecular. The type of force you see here, this is called intermolecular. We call this intermolecular force of attraction. Whereas if I have water molecules such as this, hydrogen, and oxygen being most electronegative, positive, positive. This is called intra. This is called intramolecular force of attraction. So when you see these type of forces I do have here, London dispersion forces, hydrogen bonding, London ion dipole, or ion-induced dipole, those are the molecules, or I mean the forces which exist between two separate molecules, whereas intra is just within the molecule. All right. So pay in mind there are 4 types of intermolecular forces, and starting off with the first one, dipole force of attraction occurs only between polar molecules. What are polar molecules? Polar means one portion of the molecule is positively charged, the other portion is negatively charged. What that causes is what we call electronegativity. Electronegativity is simply the ability, all right? I'm just gonna define this as the ability of an atom to attract electron, all right, electrons or shared electrons towards, all right, towards itself, all right, in a covalent bond. Remember, covalent bond is a bond where sharing of valence electron by an atom in a molecule. This term here, electronegativity, means ability of an atom to attract electron toward itself. And the trend on the periodic table, all right, this is the trend on the periodic table. Let me just write that electronegativity. It increases as you go from this side, from the left of the periodic table, going to right, left to right. So this is the periodic table you see on my whiteboard. And this is the whiteboard I'm talking about, going from left to right, and decrease going down the periodic table. So the ability of an atom to attract electron, this is the format. So given a molecule, you should be able where the electrons are being pulled towards. So this type of arrangement, if you look at positive with an arrow pointing in that direction, this is the how the electrons are being pulled. I can tell that an atom on this side is more electronegative compared to what I do have here. Example is hydrogen fluoride. All right, hydrogen fluoride, HF, like that. Hydrogen on the periodic table, there is fluorine on this side, there is hydrogen on this side. This is the most electronegative, and I can tell the arrangement will be like this. Fluorine, hydrogen, and this, if this is one molecule and the other molecule is in there, there is a force of attraction in there. There is a force of attraction in there, and we call that we call this dipole, dipole, dipole. So the key thing here is to look at the molecule and see if it is if there is an even sharing of electron. If it is an even sharing of electron, you make a conclusion that the molecule will have a dipole, dipole, dipole attraction because of the polarity from the word pole, positive and negative. An example you see here is a molecule with positive, negative, and if you look at negative and positive, they do attract one another. The green dashes and the red, if you follow the red and the green, it is a type to positive, negative, positive, negative. We call that type of attraction dipole, dipole. It's a mixture of repulsive and attraction, but overall positive, positive, negative, negative to repel, but positive, negative to attract. Okay, there is a net attraction. There's a net attraction. That's all about dipole, dipole. There is, I want to get real quick to the hydrogen bond. Hydrogen bond, from the word hydrogen, there must be an hydrogen bonded to the most electronegative. This is an example of hydrogen bonding, bonded to. That means hydrogen is bonded to fluorine, hydrogen is bonded to oxygen, hydrogen is bonded to nitrogen. These are the only elements you'll see associated with hydrogen bonding. I always say this is fun, F-O-N, fun. Other than that, if there's no force of attraction, for example, the attraction between hydrogen and carbon, this is not hydrogen bonding. It got to be the three elements listed in there, that special type of dipole, dipole. In this case, we have only the three elements you see, that is hydrogen, attached to oxygen, attached to nitrogen, or fluorine. Only those three types of element constitute what we call hydrogen bonding. This is a special type of dipole, dipole, all right? Special type of dipole, dipole. That is, look at the molecule and say, this is what it is, okay? An example here is H2O. If you look at water molecule here, it is associated, oxygen is associated with hydrogen of the neighboring water molecule. Special type of dipole, dipole. If I look at hydrogen fluoride in H2O, fluorine is attracted toward to hydrogen on the neighboring water molecule. This is an example of hydrogen bonding. There is oxygen, hydrogen, there is fluoride, or I mean fluorine, hydrogen, and there is nitrogen, hydrogen. These are the only three elements on the periodic table used to define the hydrogen bonding. Okay, by looking at the molecular structure of a compound, you should be able to tell that hydrogen bonding is in there. For example, water molecule has, or water molecules in a sample of water. For example, this one, I can tell you that the predominant type of intermolecular force is hydrogen bonding. Hydrogen bonding. It is responsible for expansion of water as it freezes. You know, during winter time, maybe you are aware or maybe you are not aware, but sometimes they recommend that you have to open your faucet in the kitchen so that the water can drip a little bit to avoid freezing. Otherwise, if it freezes, it will pass. I mean, the piping in your house will pass. Because of what? Because of hydrogen bonding. I don't want to get in details on how that works, but what's responsible for passing of the pipes during winter is hydrogen bonding. Now, that type of bonding is London dispersion forces. It is credited to scientists by the name London, who came up with this, or who discovered this type of force. And it's a temporary, all right? It is a temporary dipole. Remember what I just explained to you in terms of dipole. It is uninduced. It's not permanent. Let me just say this is induced. You can say induced. All right, induced. Induced dipole. Induced dipole force of attraction. For example, molecules such as bromine, okay, is a diatomic, or even maybe hydrogen or fluorine, diatomic. There is equal sharing of electrons, all right? There is equal sharing of electrons. However, at some point, the electrons might be delocalized, that you have more electron on this side, making this portion partially positive. This is partially positive, this is negative. And if I have another molecule on this end with, all right, if I have another bromine molecule in the neighboring, this is wanted to that, and being here negative, and this is positive right here. This force of attraction here, all right, this force of attraction here is, all right, this force of attraction is what we call induce, or just induce dipole, which constitute what we call London dispersion forces. You can see that what is going on in London dispersion forces, if they are equal, what? Equal sharing of electron, but at some point, it might be delocalization of electron. This type of force is virtually present in all substances, all right? It is present in all molecules, rather, to operate in all of them. So it has to do with polarity of molecules. Here is an example on what or how the dipole, because of polarization of the molecule, at some point, you see this portion, the more blue one shows electron-rich portion of the molecule. This is electron-rich portion of the molecule, positive and negative. Remember, this is temporary because electrons move constantly around the nucleus, and that was constitute London dispersion forces. Lastly is ion dipole. But before we look at that, because of the intermolecular forces, different compounds have different boiling point. They might have the same thing. For example, here you see 68 because of those lambda dispersion forces. So let's see ion dipole, all right? Ion dipole is basically when ionic compound dissolved in H2O, all right? There is an ion, it could be sodium chloride dissolved in H2O. I could have sodium what? Sodium chloride dissolved. It will produce sodium ion, which is positively charged, and chloride ion, which is negatively charged. The way molecules surround the ions, the force of attraction between these two is called the ion dipole. This is a dipole. This is ion. So the type of attraction here, we call it dipole, ion force of attraction when an ionic compound is dissolved in H2O. Those are the 4 types of interaction you should be able to read, especially for your lecture. You need to be well-rounded in understanding. I know the PowerPoint slide might have more than what you need for this lab, but you should be able to explain in details for your course. If you're taking the lecture right now, it is important to thoroughly read the background. I'm gonna post this PowerPoint slide, and you should be able to read more. Let's see. I'm gonna talk about the how to draw the Lewis structure for molecule later on, but I don't want to just go in details into that before I walk you through the experimental setup. Now, effect of intermolecular forces, all right? Effect of intermolecular forces on physical properties. Compressibility, all right, is one physical property. You know, when you compress something, you put it together. For example, why is it that you cannot compress solid, but you can compress gases? Because the force of attraction between gas molecule is negligible. There is large intermolecular forces. No, there's negligible force of attraction between gas molecules. They are highly compressible. Because of that, molecules are far apart. You may have seen also the rate of diffusion depending on the liquid. If you look at gases can diffuse faster than what? Faster than liquid. What you see is a red sphere is a molecule diffusing from one end to the other end. For gases, it can diffuse fast. For solid liquid, it will take some time because of the intermolecular forces before it gets out. So the bottom line, if they are starting at the same position, all right, we can say that gases will diffuse faster because of, all right, because of the effect of intermolecular forces, movement to spread out. Not effusion, you're gonna read about that, but diffusion. Diffusion for gases is faster than liquid, because solid cannot diffuse. One other physical property you need to reconcile within the molecular forces is volume and shape, all right? Solid retain their shape, right? Why do liquid do not retain their shape? It's because of the intermolecular forces. Gases expand to fill the container. That's another effect. Surface tension. You have seen an insect, say for example, a mosquito can perch on the surface of H2O is because of the surface tension, the attraction between the neighboring water molecule on the surface. This is also responsible for the beading. Have you ever seen when you wax your car and start raining, you see beads of water forming or droplet forming on your windshield? Is because of surface tension. The wetting also has to do with the intermolecular forces. If I look at these states, H2O doesn't, the water spread out faster than when you have compared to ethylene glycol. You look at this, they have same intermolecular. If they have the same intermolecular forces, they tend to fast. For example, oil will not spread out on a piece of glass because of the type of intermolecular forces. Greater similarity of attraction forces the liquid to yield, all right? Now, viscosity, you know what viscosity? Stability of a liquid substance to flow. A more viscous substance will tend to resist, all right? Will tend to resist flowing. Syrup, for example, is more viscous than H2O. It's because of high viscosity. Viscosity is associated associated with the intermolecular forces. This is what I was talking about, the second part of the experiment. You will be expected to draw the Lewis structure of the three substances. You'll be expected to draw the three Lewis structure. I don't know, you may not be able to see. Here I have the Lewis or the data sheet showing you how to draw the Lewis structure. I mean, you are expected to draw the Lewis structure of alcohol and H2O and acetone and state whether it is polar or non-polar, polar or non-polar. Well, I'm going to show you, all right, before we embark on the part one, all right, let's look at how to draw the Lewis structure for molecules. First of all, Lewis is an American chemist who proposed that when elements react, all right, they use their valence electrons. And you know, from the periodic table, you can predict the number of valence electrons for main group elements. So how do we draw the Lewis structure for molecules? Here are the rules. Here are the rules. You have to count what? Count the total what? Or determine the total number of valence electron in a molecule. I'm gonna use methane, for example. Let's try use CH4. This is methane. How do we find the number of valence electrons? Look at the periodic table. Carbon has 4 valence electrons. It is in group 4. And I have only 1 carbon in this molecule. Hydrogens. I have 4 hydrogens times 1, so I have 4. So I have 8 what? 8 valence what? 8 valence electron. 8 valence electron. 8 valence electron. Rule number 2 in this is to find out. All right. Rule number 2 is draw the skeleton of the what? Of the molecule. Skeleton of the molecule. How do I know? The first element is always going to be at the center. In this case, this is my skeleton of the molecule. All right. H. What is the structure? The skeleton of my CH4. Rule number 3 here is subtract the bonding electrons from the total valence electrons and distribute the remaining electrons on the external atom, on the external atoms, such that the octet rule is obeyed. All right. So you want to distribute the remaining electron in such a way that the outermost or the external atom satisfy or obey the octet rule. That means they should end up with 8 electrons. So let's see. Our total valence electrons here, all right, 8. Subtract the bonding electron. Bonding electron, these are the bonding electrons. And each line, remember, each line represents 2 electrons. So I have 1, 2, 3, 4. I have 8 electrons used. 8 electrons used. So I'm gonna subtract 8, and if I say 8 minus 8 remain 0. So I don't have anything to give to hydrogen. If I had subtracted the bonding electron, I'll keep hydrogen external. For other atoms, of course, they should end up with 8. But hydrogen is the only exception you do not keep, except maybe even I should put here that except hydrogen. You don't keep hydrogen electrons. If this was any other element, I'm just gonna keep the remaining electron, all right? Having done that, you now convert your lines to dots, all right? Lines to dots, and I have that as my, this is my dot, Lewis dot structure for what? Lewis dot structure for methane. Lewis dot structure for methane. So for your case, you will have to draw for only three compounds: water, isopropyl, and acetone. If I look at the last two, all right, they are organic molecules. What are organic molecules? That means they have a long chain, all right? They have a long chain backbone of carbon. For example, how will you proceed with something like the C3H8? C3H8. This is an organic molecule. The way you approach organic molecule is you draw the backbone first, all right? This is the structure, 3 carbons. And I'm gonna have remember carbon form 4 bonds. I'm just drawing the structure, the skeleton. How do I know that it look like that? It's because carbon form 4 bonds, and each one of them in this example has 4 bonds. From this chemical formula here, she'll have 8 hydrogen, nothing remains. I have the skeleton. So this is going to be the dot structure for propane. This is propane. These are the shared electron. These are the shared electron. Hydrogen, 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 hydrogen. All right. That is the Lewis structure for propane. Let me show you an example where the external atoms end up with electrons. External atom ends with electron. For example, a hydrofluoric or hydrogen fluoride, good, that's HF. How do we draw the Lewis structure? Rule number one, calculate the total number of valence electrons. This one, hydrogen is 1, fluorine is in group 7, so it has 7, and this one have 8 valence electron. 8 valence electron. Rule number 2, draw the skeleton of the molecule. This is the skeleton of the molecule, all right? Subtract the bonding, so I'm gonna subtract 2. I've used 2 right there. Remain what? Remain 6. Except hydrogen. Hydrogen does not, when form bonds, doesn't end up with 8. So this one needs 6 more. It has 2 right now here. So this one needs 2 more, 6 more. So I've used 6. If I draw the dot structure for that, you will see that it is like this. This is the dot structure for hydrogen fluoride, and here is shared with this. This is sharing with that, and this one as well. All right, you see how the electrons are shared. That's how you will draw the Lewis structure for the 3 please. You'll also have to state whether it is polar. I talked about polarity earlier on. All right, make sure that you draw you indicate the number of valence electrons. This is useful. I have more information here than you may need. Just look at what we went through. All right, this is a more detailed procedure or step for drawing the Lewis structure. All you have to do is only for the 3 substances you'll be working with. This is what I was talking about, to find the valence electrons, how to keep the external, how you subtract that, and then end up with 3 valence electrons. With that, I just want to all right, I just wanted to end up this presentation on PowerPoint slides. You're gonna read more on this. What I want to do is fast forward to the procedure for your for the experiment. I believe it's right here, which according to the handout, you should have safety cargoes, all right? The thermometer, you should have received that. Mine is slightly different, but I think there is a smaller one, all right? This is one I do have in my office. I'm in my office right now. And I think yours should be a small one. You should have received something similar to this, and there is a thermometer in its storage. You can see that, all right? So here is the stopwatch where you're gonna be recording the rate of evaporation, the filter paper, and please have a pair of scissors to cut the filter paper to size. All right, you can use a cut tape. You can have distilled water, of which you're gonna put it in 3. You're gonna put it in 3 cups. You can reuse this, or you can use the smaller one. I have smaller one, doesn't really matter. So you can label this into 3, 1 for acetone, 1 for H2O, all right, and the other one is for isopropyl. And label them, please. Label them. You will cut to size, all right. You'll cut to size. You'll cut to size the filter paper and use the tape, all right? So if this is the filter paper, I'll cut it to size. I'll now put it in the tight at the end of thermometer, all right? This is how it look like. You may use the tape it in here so that you're gonna be immersing it on to your test solution, all right? Rubber pumps, not necessarily. If you have, that's fine. It's just for tying the filter paper on the thermometer. But if you can use the Scott tape, it's well and fine. Remember, the key thing for this experiment to be successful is it should stick on the tip of the thermometer, so that when you put it in your solution, in your substance H2O or isopropyl alcohol, it should go all the way in there, should go all the way in there, so that you have that. Now, having said that, all right, you're gonna need a pen that is for later on. Paper towels, right? It's gonna work for all those. So for part one, all right, for part one, you will predict the polarity, which molecule is polar, which one is non-polar. Remember, the polarity has to do with the electron distribution, which one is more polar. I'm gonna pull electron to a side. There is an equal sharing of electron, the molecules is more likely to be polar. An equal sharing leads to polarity. Equal sharing makes the molecules non-polar. Now, you will look at the relationship between the change in temperature. This change in temperature is between the initial temperature and the final temperature once the rate of evaporation is complete. So you're gonna cut to size, all right? You're gonna cut to size the coffee cup, all right, square piece. You might have a square like this. You may not see from there, but this is just an example of the square piece. This is for just using the rubber band or scattered onto. If you look at the diagram right here, this is the square. You may not see the rubber band and the scattered to put it on. It should be hanging, all right? Don't just lay it on the table, because the table will increase the rate of evaporation, so it should be suspended on the edge of the table. You will monitor the rate of evaporation and record the initial time when you remove until the temperature become constant. Somewhere here it's talking about recording the maximum and the minimum for each substance. Look here, number 8. Once you record the temperature here, let me show you. Fast forward to data sheet. Right here, this is where you will record the minutes after every 30 seconds, I believe. After every 30 seconds, right here, step number 8. Step number 8 here, for each substance, prepare a plot of time versus, temperature versus, and determine the maximum and the minimum. Please, when you draw your graph, you should have, say, temperature, all right? Temperature, you'll see from here. Let me just put this right here, right here. So this is what I'm saying in terms of, this should be temperature versus time in minutes, all right, of acetone. I'm just giving you an example. And then you're gonna throw to scale, all right, throw to scale half temperature right here in degrees Celsius and half time on this side in minutes. Include the units. Don't just assume that the instructor will know that the x-axis is in minutes and y-axis in degrees Celsius. It may assume something like this. I'm just giving you an example on, hypothetical. It might look like that. Try your best. This is the minimum, all right? Here is the minimum, and here is the maximum. That will help you in determining. If you look at the data sheet here, it's talk about the minimum and maximum, all right? Acetone, minimum and maximum, minimum. What is the change in temperature? What is the change in temperature? You will do that for acetone, for H2O, all right, and isopropyl. So you're gonna repeat the same thing for the 3 substances and find change. This means change. All right, this means change. You know what it means, change in temperature. That means maximum minus the minimum. Maximum minus the minimum. You will do for both so that you, this is just for time, change in time. And then lastly is investigating the influence of intermolecular forces on surface tension. Gonna read surface tension. It is in my PowerPoint slide. I'm just gonna post that. And in this section, you will need the drawbars, all right? You should have the drawbars calibrated, it doesn't really matter. And I'm gonna use an object here, which assumed to be the penny. Let's talk about using the penny. That's the purpose of the penalty you are asked right here. This is the penny you need in that step, the last step, of which the direction place a dry penny facing down, all right? And you'll gather all these what you need, isopropyl, water, and acetone, and you're gonna put it, all right, you're gonna add drop by drop using the droppers. You may not see from there, but this is the dropper. See the dropper? You're gonna use, if this is my and I'm just gonna count how many drops of liquid that a penny can hold before any of the liquid falls out onto the table. So you will count and record how many drops on the data sheet. So here, how many drops, trial 1, trial 2, trial 3, and then you find the average. You'll do for what, isopropyl, and then you do for that. Remember to stay away. Don't do it in your, next to your open flame. This is flammable. I don't want you to burn your house. So that's what you'll do for the last section. You'll do the same thing for acetone, for water, and examine that. And please, I know you just received, some of you just received yesterday, some of you received yesterday your lab kit, and probably some of you received today. I will give it until next week for you to turn in this lab, but if you can go ahead and turn in before the before weekend, or by next week, that's fine. I mean, for lab number 1, this one you can turn in next week. You have 1 week to turn in this lab. I know some of you, I don't know, I'll find out tomorrow if you are yet to receive your lab kit, but last week is due next week along with this lab. I'm sure by Friday, you should have received your lab kit if you ordered it right now. I received mine today, all right? I have mine here today. So I called the company and we are all good. With that, I just want to stop sharing the screen. Tomorrow, I'm gonna be available during the lab time. If you have any question, just stop by. But I'll recommend that, just show up for 5 minutes. If you are comfortable with what's going on and you understand what's going on with the experiment, just complete the work and turn in next week. You have 1 week to turn in the work. I'm gonna send you the pre-lab for this. I haven't set the questions. You have the post-lab questions, but the pre-lab, I'm gonna send it to you so that you turn in everything through Canvas. Other than that, thank you. And I hope to see you tomorrow during the lab session, 1 o'clock to 3:40. Thank you.